Okay, hello. We done, you know that the next week on Monday, we are going to have a test. Okay, it's going to be of a test number one. We are going to have the test on, the test on Zoom. Okay, we already talked about the time for the test. So we take it to be Monday evening. Okay, between, I think I said 6 to 8, or if you need a little bit more. So we meet on Zoom and we take care of the test. The test would cover chapter 1 and chapter 2 that we did. Chapter 3 is not quite a lot. It's just a couple of sections. I'm going to talk about it today, and we may give you one question from this chapter 2. I already posted the practice test, so I posted a solution for you, and we are going to prepare for that test. Okay, so I give a summary of these two sections in chapter 3. Chapter 3 is a kind of a classic vector space that we're going to use in future. So it's a space of 3-dimensional, 2-dimensional, or n-dimensional. If you have done calculus 3, you will see these type of ideas, but otherwise not a big deal. Okay, it's just a collection of definition. Let's see how far we can go. Then we decide what are we going to do with this section for on the test. Okay, so let me see how far we can give you a kind of introduction. Okay, so maybe a combination of this section 2 and 3, if I can get this camera working. Okay, so there you are. We are going to talk about this is section 3.1. Okay, that will help us to get a better understanding of the abstract concept that we're going to have in chapter 4. When we do the example, we come back here. So we want to know what's going to be the definition of the vectors. Okay, that's going to be the one. And you know that in many applications, we are going to have, for example, in physics, we have some quantities like area, length, mass, temperature. These quantities are going to be described only by by the numbers, by the numerical, format or magnitude. So these are going to be referred to as scalars. So a scalar is something that you just give us a number. Okay, the area 20 square feet, for example, or the length. These are going to be referred to as a scalar. But sometimes there are some quantity that you are going not only to need the measurements, but also you need a direction. So if you need the measurements and the direction, the result is going to be called vectors. Okay, so two type of quantities, if you like. This is let's just give you an idea that quantities or physical quantities, if you like, physical. Okay, this is a physical quantity. Quantities such as such as area, length, length, mass, etc. Okay, these are going to be called. Okay, these quantities can be identified. Are completely. Okay, these are going to be completely described or characterized. Okay, that's going to be described. Okay, by the magnitude, if you like, magnitude or the measurements. Okay, as soon as we have the measurements of the quantity quantity. Okay, completely describe of the quantity. Okay, this type of quantities refer to it. So such quantities, okay, such quantities are called, they are called scalars. Okay, scalar just number, no direction, and no direction. But we have other quantities. Okay, we have other quantities, other quantities. Our quantities called, okay, this quantity called vectors. Vectors. Okay, so if you have a vector, you have a numerical measurements and a direction at the same time. Okay, so they are going to be described, so they are not going to be, okay, if you have this, just they are not, okay, they are not described or completely determined. Okay, completely determined until, okay, until a measurements, okay, a measurement, magnitude, and the direction is given. And the direction, okay, and the directions are given. Okay, so for example, winds, velocity, okay. So for example, okay, for example, uh, so winds, if you like, or just velocity, okay. Velocity is going to be velocity of, wind velocity is, okay, is going to be, is a vector, if you like. So for the vector, basically, you know it. We need a direction and we need a measurements. So what we are, because when we talk about the wind, we say 20 miles, okay, 20 miles per hour, northeast, southwest. So you guys give us the direction they're going to have. So basically, if you are going to have a vector, okay, so for the vectors, you start with the initial point. This is going to be A, and then you need a direction to go on. So this is going to be a direction that we're going to have. So we go from A to B. A to B, this is going to be the vector V. So in this case, this is going to be initial. Okay, that's going to be initial point of your vector. And this is going to be your terminal point. Terminal point of the vector. So the vector would be denoted, you see the vector V would be denoted by its initial and the terminal point, A and the B. Okay, and if you want to write it down in algebraic format, suppose if you are in two-dimensional, for example, if you are in two-dimensional, A is going to be x1 and the y1, and the B is going to be x2 and the y2. So in this case, the vector V, you see the vector V, which is going to be A from A to B. So this is the way we're going to denote it. So the difference between, you see the x2 minus x1 and the y2 minus y1. This is going to be called component format of the, okay, of the vector V. So it's going to be component, okay, component form of the vector, okay, the vector V. Then if you have a vector, so what we'd like to do, we'd like to get a mathematical modeling. Okay, so if you have the numbers, we can add, subtract, multiply. So what we'd like to do, we'd like to have introducing some operations. So the operation that we're going to have is going to be, you see, if k is going to be a number, a scalar is going to be a number, and V is a vector. V is going to be a vector. So what we do is we defined the k times v as the following vector, as the following following vector. So if this is going to be your vector v, if this is going to be your vector v, so k is a number, you see, you multiply by 2, you multiply by 3. If k is positive, if k is going to be positive, for example, this is going to be your vector kv. Okay, this is going to be the case for the k positive. But if your k is going to be negative, so this is going to be the vector v. This is going to be the vector v, and then in this case, in the other direction, you are going to have the k times v. Okay, when k is less than 0. So with this idea, we define the so-called a scalar multiplication, okay, on the set of all these vectors. Okay, so the other thing that we can do is if two vectors are given, we can add or subtract the vectors. Okay, so one more thing is if the vectors let's say v and w are given, okay, if they're going to be given, then the sum of the vector, okay, the sum vector. So the sum vector v plus w can be defined. Okay, can be defined. So for example, these are just geometry. In a minute, we are going to change it into the format algebraic model. We just give an idea of what we want to do. Okay, so these are just geometry. So for example, this is the way we define in geometry. So this is going to be, suppose this is the vector, okay? So suppose this is going to be the vector v. Okay, this is going to be the vector v, and this is going to be the vector w. Okay, so it's going to be v and w. So then we can define the sum of these two vectors. You see, this would be defined as the, so u, this is going to be v plus w. Okay, so geometrically we are able to find the sum of two vectors. Okay, so this is going to be the sum of the vector, and similarly we can define, okay, similarly the difference. You know that if you want to define the difference between v minus w, so what we can do is going to be, it's going to be v plus okay, negative w, because the scalar multiplication is already defined. Okay, so as you can see, this is a kind of, so therefore we have a scalar multiplication. A scalar multiplication means a number times the vector, okay? Multiplication and vector addition. Vector additions, okay, are defined. This is the plan. Okay, the plan that we can introduce these two notion, and we are going to do it when we get to the next chapter. So addition, for example, for the number is commutative, and we have some other property of the addition. For the scalar multiplication, the same thing. So that's just the motivation. So what we're going to do is we are going to start in, these are going to be, can be done in 2-dimensional, or can be done in 3-dimensional, or in general can be done in n-dimensional. So we are going to put it into the format using the XY coordinate and introducing those vectors. Okay, so that's basically what would happen if you stay in geometry. But if you want to use the XY coordinate, this is the one we call it vectors. Okay, so that's just introduction. Vectors in coordinate system. Okay, coordinate systems. Okay, coordinate system is going to be two-dimensional R2 or three-dimensional R3. We can write it in R2 and R3 and then you continue, okay? So it's going to be, let's say, vectors in we call it two-space R2, okay, and three-space, okay, R3, three-dimensional and two-dimensional. And you can do it in general. Okay, just give you an idea. So what we'd like to do is we'd like to introduce these vectors in these spaces and then introduce the addition, scaling, multiplication, and show that you're just extending the set of real numbers. You see, when you have a real numbers, you can add two real numbers to get a real number. You can multiply them together. So we are going to build up a new system. So the system is going to be start from here. Okay, so if I go with the three-dimensional, then we extend it into the n-dimensional. Okay, so for example, if U is a vector or X, and I go with the X, Y, Z, if X in R3 is going to be a vector, or a point, then you know that X can be written as, okay, X1, X2, X3. So this is going to be X1, X2, X3. Okay, this is going to be the one, you know, we consider this as a point. You know, it's going to be like a vector from the origin, because your book uses this notation for the vectors rather than, okay, this is the other one, but in this book, we're just using that notation. Okay, this is X1, X2, and X3. And we stay with this notation of your book. Okay, this comes, so if X is X1, X2, X3, then, okay, this is going to be where this X1 and X2 and X3 are numbers, okay, are going to be, okay, these are going to be called R in R, if you like, and are going to be called, okay, are called components. Okay, these are going to be components, of, okay, of the vector X. Okay, so if you get this number, then what we can do is, so we are going to denote the point in R3 using this notation, and we can use it in R3. Okay, Rn, if you like, X1, X2, X3 up to the Xn. So we pick two vectors in R3 and we introduce the sum and the scalar multiplication. Okay, so there you are. Pick 2 points. If X and Y are going to be vectors, you know, I'm just call the points in R3 vectors. Okay, in R3. Okay, so this is going to be X equal to the X1, X2, X3. Okay, and the Y is equal to Y1, Y2, Y3. So what we're going to do is we are going to define, okay, we define a vector addition, okay, vector addition X plus Y, and a scalar multiplication, and a scalar multiplication, a scalar multiplication is just a number times a vector, K times X, okay, K times X, okay, this is it as the following. They're all a standard operation. So this means if you want to add X plus Y, you just add the coordinate together, okay? So this is going to be It's going to be x1 plus y1, comma x2 plus y2, and the x3 plus y3. Okay, the sum is again is a vector. And if you want to multiply k times x, so you multiply by each component, kx1, kx2, and kx3. Okay, so that's it. We just define the new role, new operations, addition and scalar multiplication for our vector. Okay, so this is going to be the format. Now, quickly, we can prove that these operations are nice. Okay, operation of addition, follow all the additions property and the scalar multiplication, the same thing. So we can write them as a theorem. Okay, so it can be proved if you like. So I write them as a theorem here. Okay, this is a new system, so you have to build up the system, and you just keep going. You see, the following are going to be all easily seen if you like. So if you pick so suppose if you have some vectors, suppose if x, y, z, etc. are going to be our vectors, okay, are going to be vectors, and if I use something like alpha, beta are scalars, numbers, okay, are going to be scalars, then the following would happen. Those property, for example, number one, okay, addition is commutative. You see x plus y is equal to the y plus x, because this is true. Because in the definition, you're just working with the numbers. Okay, that's the first one. So the other property is going to be, that the other property is associative property. If you want to add three vectors together, you see you can add it two at the time. So x plus y plus z is going to be plus z. It's going to be like x plus y plus z. So that's associative property. Okay. Then the third one is, in addition, we always have a zero. So we can have a zero over here. Okay, if zero, which is equal to the 0, 0, 0, is the zero vector. Okay, if this is going to be the zero vector, then as usual, you have the fact that the x plus 0 is equal to the 0 plus x, and this is going to be equal to the x. Okay, it's again clear. Then for each vector, you can have the opposite of the vector. Okay, the opposite of the vector is going to be, the other one is x plus a negative x. Okay, is equal to the 0. Okay, it's going to be 0, and you know that where the negative x is just a negative x1, negative x2, and the negative x3. Okay, so these are all clear, but we just want to build up property that we're going to use in future. Okay, the other property that we're going to be interested in is the multiplication case. We have only a scalars. We cannot multiply the vectors together. So for example, if you have a number alpha and you want to multiply by x plus y, you distribute it. It's going to be alpha x plus alpha y. Okay, so this is just a distribution for the scalars. Another thing that we can have is that if you have two scalar, okay, you have the alpha times beta x. So it's going to be alpha beta, if you like. Okay, alpha beta then x. It's like 2 times, okay, 3x would be 6x. And the other things that we can do is number 7. Okay, in number 7, if you have alpha plus beta, two numbers, you can distribute it. They're all clear. But we write it down for completeness. Okay, that's going to be the one. As eventually we have the vector 1. Okay, and this is it, 1 times x would be equal to the x. You see in the next chapter, if you have a system, of vectors in general, not R3 or Rn, with the vector addition and the scalar multiplication that satisfy all these properties, that system is going to be called a vector space. So for future, not now, because we are not going to talk about it. That's why we need this one. So in general, if you like, we give you a remark. Okay, remark. And the remark is going to be, okay, by the above theorem, by the above theorem, you see R3, or in general, Rn is a vector space. Okay, a vector space is going to be, it's going to be a set of objects. We call it the vectors, and we have this addition property that we're going to have. Okay, so what we did, you see, from the system of the real numbers, we just go into the three-dimensional. We introduce something very similar to the real numbers. Okay, so what we are going to do, we are going to continue. So when we're working with the real numbers, we did have the notion of the absolute value. The absolute value give you the distance from the origin. Remember, we are going to have the same thing over here, but we are not going to call it absolute value. We call it the norm, and this is very important quantity. Okay, so what is going to be, the problem that we're going to have is going to be related to the norm for this test. Okay, so what is going to be the norm? Okay, a norm of a vector. It's the same thing. It's just a distance from the origin. Okay, so this is it. So it's going to be the distance between the distance. Okay, the distance between the initial. Okay, the initial and terminal points. Okay, of a vector. Okay, of a vector is going to be called. It's called, that the length. Okay, this is going to be the length, or in this case, or a norm. Or okay, that's it, the norm. The norm of the vector. Since in R3 we consider all the vector from the origin, so this is going to be a situation that we're going to have. You see, if we have a vector, okay, if the vector v is going to be, this is it, or the vector x. If the vector x is going to be equal to, let's say, x1, x2, x3 in R3, then, okay, the norm, okay, the norm of x, is going to be denoted, okay, it's going to be denoted by, the norm x. This is a notation, and is defined by this is a distance from the origin. Norm x is going to be equal to the square root of x1 squared, x2 squared, plus x3 squared. Okay, so that is going to be the norm of the vector. If it's going to be one-dimensional, you see, if it's going to be just r, and that give a radical x1 square. A square root of radical 1 x1 squared would be absolute value of x1. Okay, so this means you are on a right track, if you like, to get these numbers. Okay, so the norm of the vector is going to be distance from the origin. So you get a couple of problems in this case, and you have some in your practice one. So let's get this one. Okay, so the norm is going to be the distance from the origin. So they give you a couple of problems. Okay, so this is it, the kind that you have in your, okay, you have in your practice one. So suppose I go with the three-dimensional. Okay, suppose x is equal to, or yes, x would be fine. Suppose x is equal to, okay, x is equal to the 1, -2, and 3, and y is equal to -1, okay, 0, and 1. Then you may ask, to find each of the following. Okay, find each of the following. Okay, each of the following. So, for example, you may be asked what is going to be the norm x. Okay, the norm x and the norm y. Okay, it's easy to find. Okay, this is it, solution. So the norm x is going to be a square root of 1 squared, okay, plus -2 squared plus 3 squared. So 1 squared would be 1. Okay, this is going to be 1, 4, and 9. So that give you, okay, 10, 14. So we write it down as exact. We are not going to simplify it. So that give you the norm of x. Okay, so that's a norm x. So if you want to find norm y is going to be the square root of -1 squared plus 0 squared plus 1 squared. So if you substitute, that give you, if you simplified 1 plus 1, so that give you radical 2. So the norm of y is going to be equal to radical 2. Okay, so this is easily done. But suppose you want to find this one. You have some in your book, okay? Suppose you want to find what's going to be the norm of the x minus 2y. So you have to form this vector first. You have to form x minus 2y, and then come back and do the job. So this is it. Remember, this is x and the y. So we want to find what is x minus 2y is equal to. The x is 1, -2, and 3. Minus 2y is going to be 2 times -1, 0, and 1. Okay, we talk about the scale multiplication. You multiply these two first. So it's going to be 1, -2, 3. You can give a positive sign and multiply the -2 inside. So that gives you 2, 0, and -2. Okay, now add them together. If you add them together, 1 and 2 would be 3, and that gives you -2 and 1. So this is going to be the x. Okay, this is x minus minus 2y. Okay, now you want to find the norm, just use the formula. So what's going to be the norm of x minus 2y? Okay, so the norm of x minus 2y would be what? Would be a square root of 3 squared, okay, -2 squared plus 1 squared. 3 squared would be 9, 2 squared would be 4, and the 1 squared would be 1. Okay, get the same one. 9, 4, and 1. Okay, so that get you the same number. It's coincidence. So the norm of x minus 2y is going to be the same as okay. So You have some of them, we give you a couple of them. We want to know how you operate with this type of, okay? You're operating with this type of operations, if you like, to get these numbers. Okay, so what we did, we just extend the notion of the absolute value, we extended to the notion of the norm, and that enable us to be able to go on. Okay, there are many properties of the norms that we are going to check. Check later. But the first thing that we can do is, if a vector is given to, when we want to study the, when we want to study our property of the vectors, we have unit vectors are going to be very popular and very useful. So the unit vector, a vector is a unit vector if the norm of the vector is 1. Okay, and it's easy to change any vector into its unit vector. So that's another expression that we're going to use. Okay, so let's define what is unit vectors. Okay, unit vectors. That's it. A vector x with norm x equal to the 1. Okay, is going to be called, it's called a unit vector. Unit vector. Okay, so this is going to be the case, the unit vector. If you are in three-dimensional, we have three famous one. Okay, so in R3, in 3 space, or in R3, the common vectors, they are very standard. We're going to use quite a lot these vectors. The unit, okay, the unit vectors along, okay, along the x, y, and the z-axis, okay, and the z-axis are going to be denoted, you've probably seen it before, denoted by, okay, that's it, denoted by I, J, and K. Okay, denoted by I, J, K. Okay, these are going to be known respectively. So this is what we have. We have I is equal to 1, 0, 0. J is equal to 0, 1, 0. And the K is equal to 0, 0, 1. Because standard unit vectors, why we are interested in this type of quantities, because we can write down, you see, this is it, note that each vector in R3 can be written as a combination of these three. Okay, note that if you have the vector x, which is going to be x1, x2, and x3, you see that's 1. So we can rewrite it as x1 is a number, x1 times 1, 0, 0, plus x2 times 0, 1, 0, and the x3 times, x3 times 0, 0, 1. Okay, you know that this is going to be x1 times I, x2 times j, and x3 times k. So the vector x can be written in this, in this format. It's popular form, so you got to know it. Sometimes in some classic example, they give you in this format. So we are ready for it, and we are ready to know to work with both type of notations. Okay, so for example, if x is equal to, let's say 2, 3, and -5, then the vector x is going to be of the form of 2i plus 3j minus 5k. Okay, so this is going to be another, just a step by step, introducing these type of notations that we may use in future. Okay, now there is something interesting that we are going to use. You see, if you want to study the space of these vectors, it's easier to study the unit vectors. Okay, we know that the unit standard one is ijk, but if a vector is given to you in general, you can change it into the vector space. This procedure is important and use it. We call it normalizing a vector. Normalizing a vector means the vector is not a unit vector, but we are going to introduce, change it into the unit vector, okay? So we must know this expression. So the expression is, what is normalizing? Okay, what is going to be normalizing a vector? Normalizing a vector, change it into the, okay, unit vector. This is it. If x is, of course, a non-zero, is a non-zero. Okay, if it's going to be a non-zero vector, then, okay, then u equal to x over norm x. You see, because if it's unit vector, norm x is 1. If it's not, it's something less, it's 2, 3. So we divide it. If you divide the u by x by norm x, this is going to be a unit vector. Okay, is going to be a unit vector. Okay, it's going to be a unit vector with the same direction, of course, with the same direction. Okay, with the same direction as x. And this process is called normalizing, okay, that you change it, okay, this process that we have, okay, this process is called, we're going to call this one normalizing, okay, normalizing the vector x, the vector, okay, the vector x. So it's not a big deal. If the vector is not a vector space, we can quickly change it to the, okay, change it into the unit vector. Okay, we do it from time to time, and this is an example. So example is, you want to find the unit vector. Okay, find the unit vector. Okay, find a unit, the unit vector that has the same direction, that has the same direction, the same direction as x equal to, the 2i plus 2j minus k. You see, so this vector is given to you. This vector is not the unit vector. You want to normalize it. Find the norm, then divide the vector by that norm. Then it's going to be normalizing. Okay, so the norm, this is the vector. So that is going to be the solution. The solution is your vector with, okay, just repeat it here so I have it. So x is 2i, okay, 2i plus 2j minus k. So it's the same as 2, 2, and the negative 1. Okay, so find the norm of this vector, the norm of x. So the norm of x would be what? Would be the square root of 2 squared, okay, 2 squared, and the negative 1 squared. So the 2 squared would be 4. We get the 4 and the 4 and the 1. So that gives you radical 9, which is equal to 3. So the norm of your vector is going to be equal to 3. Okay, go back, normalize your vector. So the normal vector is, the unit vector would be x over the norm x. So it's like a 1/3 times the one that you have, okay? Different format. You have the 2i, 2j minus k. Multiply it. This is going to be 2/3 I plus, okay, plus 2/3 j and minus 1/3. So that gives you the unit vector. Okay, so it's not a difficult procedure, but these are the one that from time to time we are going to use. Okay, so just want to just briefly give you the things that we need, okay, for future, because we need this classic example really to be able to change it to the abstract form. This is all you need from this section 3.1, if you like. Okay, the reason that we study this one is just we have, you see, we didn't talk about the multiplication here. Okay, there are a couple of multiplication of the vectors, but we are going to be interested in just one of them, and that's the inner product or the dot product. And this is in section 3.2, and then you don't need anything else from this chapter. Okay, let's give it this definition. 3.2. We want to know what's going to be the inner product or dot product, different names. Okay, what is dot? Dot product. Dot product. Other names are inner product, inner product, okay, or a scalar product, a scalar product. But inner and the dot is the most popular one that we use. Okay, now what's going to be inner product? This would be used quite a lot, okay? So this is it. If two vectors are given to you, so if x equal to the x1, we are saying the three-dimensional, okay, x1, x2, x3, and y equal to, okay, y equal to the y1, y2, and y3 are going to be vectors, okay, are going to be vectors in R3. Then the dot product, then the dot product, okay, dot product of x and y is going to be denoted by, you see, this is it, x dot y. You have to write this dot, okay? It's not like a multiplication that you have in algebra, you just write x, y. No, x, y doesn't mean x dot y. Okay, make sure you write it down. Okay, so it's denoted by x dot y and is defined by, okay, defined by, this is it, x dot y. Okay, it's going to be, you see, x1, y1, x1, y1 plus x2, y2, x2, y2 plus x3, y3. Okay, you see the term to the right, they are all numbers. So this product is not a vector. You see x dot y is a number, is not a vector. Okay, so, you know, in general, if you have it in n-dimensional, you can write down as a sigma form, but we don't need it now. Okay, so just note that. Just remind you that, note that x dot y is a number. is a scalar and not a vector, not a vector. Okay, vector in this case in R3. Okay, you have a couple of questions related to this one, so you got to be careful. Okay, so the dot product, this would be extended later on. We have inner product space in linear algebra, quite interesting arguments, and you will see in future such an important concept. That's why we introduced this one now. We introduced to get the feeling first, and then we extend it at the end of the course. Okay, example, this is it. 2 points would be given. They ask for the dot product. So the example is going to be if x is going to be a vector, it's a 1, -3, and 4, and y is equal to 1, 5, and 2. If this is going to be the case, then what's going to be your dot product? Then x dot y, you see x dot y is going to be equal to multiply. It's going to be 1 times 1, okay, -3 times 5, and plus 4 times, okay, 4 times 2. Okay, so multiply them together, so this is going to be equal to 1. It's going to be minus 15, and this is going to be 8. Okay, so that give a 9 and a -6. So x dot y is going to be a negative, okay, a -6, and then with that. Okay, it's not a big deal, but it's quite popular. We call it a product. So how far you can go as a product, okay? So the property of the inner product, okay? So this is going to be the case. And we write it down as a theorem. And this theorem is going to be used, okay? Theorem. So what is going to be this theorem? Suppose you have vectors. You see, suppose x, comma y, and z, for example. These are going to be our vectors. Our vectors in R3. Okay, and k is a number. And k is a scalar. It's going to be a scalar. Okay, if this is going to be the case, then we are going to have the following. Then the first property is that this scalar multiplication is commutative. X dot y is equal to the y dot x. Because you see, the way we multiply, we just multiply the numbers together. You see, we multiply those components, coefficient, coordinates together, they are numbers. So it's commutative. Okay, and this is associative. So x dot y plus z is going to be x dot y plus x dot z. See, so commutative, associative. Next, the number 3 is if you have a number, you see, is k times x, 2x, 3x, dot y. You can pull out the k, or you can move it. You see, you can write x dot ky, or you can write down as a k times x dot y. You see, very easy to prove. The important part is this number 4. The number 4 is that x dot x is the norm of x squared. You have a couple of theorems and we give you one question anytime you want to prove something. If you want to evaluate x dot product, just go with that formula that you have. Okay, you know, x1, y1 plus x2, y2. But if you want to prove something, you just use this one. X dot x is norm x all the square. I'll show you where we get to the solution of those problems. Okay, and this is going to be the one. And the other one is that and the number 5 is clear. If the product is 0, you know that the norm would be 0. So this means your vector must be 0. Okay. So these are some properties of the inner product. Okay, a space that we are going to have. Now we can put them together and get more. Okay, get more results of this. Okay, this relationship between the norm that I'm going to write it down for you. But first we need, you see, there is a concept of orthogonality. See, two vectors to be perpendicular or two vectors to be parallel. We want to find that one, and that's we need this type of ideas. So to get to that one, we want to know what's going to be the angle between vectors. Okay, so these are a standard operation that we can use. And what is angle between vectors? That give you a very famous result, and then we are done almost. Vectors. Okay, so what's the idea? The idea is you are going to have two vectors. You should look at this one. This is the vector x, and this is going to be the vector y. There is an angle here, theta. We want to find it. We want to get the formula to find this one. So what we do is we are going to get this one. Remember, we talk about the adding and subtracting. If you get this one, since the direction are going to be different, this is how you end up. This part is going to be x minus y. Okay, so this is going to be x minus y. Okay, and so what we are going to do is we have a triangle here. So we are going to borrow a formula from geometry to get this angle. There is a formula in geometry, we call it the cosine of the angle. And we can use it to get this idea. Okay, so this is, I write it down, then I can show you and prove it for you. So what's going to be the angle between the vectors? If theta is going to be, is the angle. Okay, it's going to be the angle between vectors x and y. Then I'm going to find this angle. We have a cosine formula. It's a cosine of theta is going to be equal to x dot y over the norm x times a norm y. You may be surprised, but I'm going to show you how you arrive at this formula. You see, we need it because if they are going to be perpendicular, this theta would be 90 degrees. And the cosine of a 90 degrees is 0, so x dot y would be 0. That's why we need it. You know, we don't have to prove it, but if you want to prove, you see that you have something in tricks, trigonometric functions, that this is the data, okay? And so the theorem is that a square of the side opposite to the data. Let me write it down. So if you like a proof, note that. We just take it as a definition, but if you like the proof, the norm of x minus y squared, that's the square of the size here. Okay, the square of the size. Okay, the size is going to be just the norm. Okay, this is the size, and this is the length, and the length. Okay, so you can use that theorem from geometry, that the square of this size is going to be equal to the size of the other one. So norm square x squared plus the norm of the y squared minus twice of the norm x times norm y and the times cosine of the data. They call it cosine formula. Okay, they call it cosine formula in tricks property that we're going to have. Now, if you open up these numbers that you see over here, you see, just to complete the proof for you, you see I can expand this one because the norm is x dot x. So what can I do is, so we say that, the norm of x minus y squared is equal to the x minus y. Anytime you want to prove something with the norm, start with the norm square and write it down as a dot product. So dot x minus y. Distribute it, foil. But keep the dot. X dot x minus x dot y minus y dot x plus y dot y. Okay, as a dot product. X dot x would be norm x squared. Okay, these two, remember, it's commutative. X dot y and the y dot x are the same, so that give a negative 2x dot y. And this would be norm of, okay, this would be the norm of the y squared. See? If you put it here, so what's going to be the result? So the result is going to be, see, put it here. So what we have the norm of x squared, okay, minus 2x dot y plus norm of the y squared is equal to the other side, norm of x squared, norm of y squared, minus 2 norm x times norm y, cosine of the data. You see? These would be all cancelled out. So what's the conclusion? The conclusion is going to be negative 2x dot y is going to be negative 2 norm x and norm y. Okay, norm x times norm y, cosine of the data. If you solve for the cosine, you get the formula that we talk about it. So cosine of the data is going to be x dot y, norm x, and norm y. You don't need to know the proof, but the techniques help you to solve. Okay, we give one problem to prove regarding the norm. You have a couple of them in that practice one that I gave you, and I'm going to give you the solution of all of them. All of them are going to be solved with this formula, all of them. So that's why I just give you this one so that you get the idea. So expand this norm of x minus y squared, x plus y squared, then you'll be able to simplify it to get these angles. Okay, so the reason that we introduced this one really is not that we be interested in finding the angle, but if data is going to be 90 degrees, then x dot y, let me just give you the conclusion of this theorem. Okay, so the remark, I just want to make this remark, that's why I introduced this one. So what is going to be the conclusion that we are going to be interested for future? That's it. So just number one, you see the number one is going to be if data is going to be equal to the pi half, then the cosine of data, cosine of the pi half, data would be 0. So what we have 0 equal to x dot y over the norm of x times the norm of y. You know that this means the top must be 0. So x dot y would be equal to the 0. So two vectors are going to be perpendicular or orthogonal if the dot product is equal to the 0. As we need this one to know it, okay? So two vectors, x and y are perpendicular, perpendicular, that's the expression, or orthogonal, orthogonal, if and only if the dot product x dot y would be equal to the 0. We take this one as a definition in linear algebra, but I just wanted to see it really, to see what would happen for this formula, this famous formula. So you have to know it. If they say x and the y are a perpendicular or orthogonal vector, so you know that x dot y is equal to the 0. We are going to extend this concept of the orthogonality later on. It's going to be very abstract, but now we want to see it because it's easy in in Euclidean space, we got it. So that's one. The other one is, again, for your interest, is going to be, if this data is going to be, if the data is going to be equal to the pi, if you like, it's going to be pi cosine, but the pi is pi or 0. The cosine would be, if it's going to be pi, so these two vectors are going to be the same, or they are going to be called parallel, So two vectors, I'm not going to use it, but two vectors, x and y, are going to be parallel, if the angle in between is either 0 or it's pi. When it's a 0, both of them are the same. If it's a pi, the other direction, if you like. You see, this is the vector that we're going to have. So this is going to be 0, and this is the other one, They are going to be, the same, if you like. So that's when the data is 0, and this is where the data is pi. That is going to be the case. But the most interesting one is part 3. Part 3, that give a very famous inequality. If you want to continue studying advanced linear algebra, this inequality is very important. You know that the cosine is between 1 and -1, or the absolute value of a cosine is always, note that the absolute value of a cosine of the data is always less than or equal to 1. So get your formula. So what's your formula? Cosine of the data is equal to the x dot y, and that was the norm of the x times the norm of the y. If you take the absolute value of these two, absolute value of a cosine is going to be the absolute value. The top is going to be x dot y because it's a number. The bottom one, you don't need any absolute value. So this must be less than or equal to 1. If you cross multiply, so that give a very famous inequality. I can prove this one, using other methods, but we just leave it. You see, this inequality is such an important one. This is the shortest proof, you can get. The absolute value that, you see, x dot y is a number. So we can take the absolute value, norm x, norm y. This is a very famous inequality in algebra or in mathematics. We call it Cauchy-Schwarz inequality. It can be proved using different methods. And not only for these vectors, you can prove it in calculus, a different format. And so there are various forms of this one. In your book, they call it Cauchy-Schwarz. Okay, that's it, Cauchy-Schwarz. Schwarz inequality. Just know it by name. But there is another version, that was also proved by a Russian mathematician. His name is Biankovsky. So we usually refer to this inequality as CBS. Okay, this is it, CBS inequality in mathematics. So it's a stand for the Cauchy, Biankovsky, and Schwarz inequality. It's just a starting point, really. It would have many, many other properties of this, okay, of this CBS equality. So I just use this, and this was just an excuse, really, an excuse to introduce the orthogonality. Okay, I could done it a different way. I could just write the definition for you, but what I did, I just used this nice, the angle between the vectors. And the Cauchy-Schwarz is going to be used quite a lot in future if you go with the advanced type of linear algebra, really. And but we need to know it, and then you can go on forever. You can prove any geometrical property of the Rn in the Euclidean space. I'll just give you one of them, and then there are a couple of them in in your practice one. Then we are going to do it. You see, for example, remember you have the Pythagorean identity. So we may ask you to prove this one. You see, if you have two vectors, so just make it a theorem. Okay, the theorem is kind of Pythagorean. Okay, this is going to be one Pythagoras, theorem, or Pythagorean theorem. Okay, this is it. You see, if it's one vector, we call it norm x, and you have another one. This is going to be norm y, and they are perpendicular. Okay, so what's going to be this one? Their addition. This is going to be norm of x plus y. You know that the norm of the square of the hypotenuse is the sum of the square of the other two. You see? That is going to be the version of this theorem in norm. Now, how are we going to prove it? We may ask you to prove this one. I told you, anytime you want to prove anything about this, you see, expand this one. Change it to the dot product. That's automatically we get the results of the proof. You see, the norm of x plus y all squared is going to be equal to x plus y dot x plus y. That's the best way to prove all these theorems, any there. Distributed FOILet. Remember, dot, dot, dot. Some people, they drop the dot in the solution. We don't accept it because it must be dot. Okay, x dot x, x dot y, y dot x, y dot y. You see, x dot x, we talk about is a norm x squared. These two are commutative, so x dot y and the y dot y is the same. So that gives you 2x dot y. And this is going to be norm of y squared. But we know that the x and the y are orthogonal. I have, I didn't complete the, okay, I'm going to write it down, sorry. I just give you the triangle. Let me finish it, then I come back. You see x and the y are perpendicular, so x, so you say that x and y are orthogonal or perpendicular, orthogonal. And so x dot y is equal to the 0. Okay, so this is 0. So this is it, you proved it. Norm of x plus y squared is norm x squared plus norm y squared, and then do that. Okay, so I have to add here, I just describe it better. So if the vectors x and y, of course, are orthogonal, are perpendicular or orthogonal, then we have the Pythagorean identity. Okay, very nice result. Okay, and anything you want to prove regarding this norm, just expand this one. As is a stand, you see, if you want to evaluate something, use those formulas, the square root that we have. But if you want to prove something, you have to change it into this form to be able to do it. Always the norm square is the dot product. It's going to be a dot product. They expand it quickly, you will get the result. Get these numbers done. Okay, so this is all a summary of what we need really from this chapter. We need you to know a couple of these ideas in the Euclidean space, we call it. You know that the R3 with this norm that we define, or with this inner product that we define, we call it three-dimensional Euclidean space. Okay, or in general, we call it n-dimensional Euclidean space. Why? Because with this norm and this inner product, all the theorems in geometry can be proved here, or can be extended here. So that's why we call it Euclidean, n-dimensional space. Okay, so you should be ready to take that practice one. Okay, I'll post a solution for you. Okay, and we just leave it to see how we can give you that test on Monday. If you have any difficulty arranging the time, okay, let me know. Then I can, give you an alternative time to take the test. But officially is Monday. Okay, it's Monday. We start at 6 o'clock in the evening. Okay, 6. We go on 6 to 8, 8:30, or even to the night. Give you time to do it. Okay. So if you need any alternative time and some difficulty to manage it, just send me an email. Then we can talk about it. Okay. So I put those practice one. If we need it, I can give you another recording if you like. If you need help, need Zoom meeting, anything, you have to send me an email before you come. Send me an email, we arrange it, and we come and we talk about it. Okay. So have a good one, and take care. I will post this one, so bye-bye.